everyone, and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Jennifer Nyman. I'm a senior engineer at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of CERDP and ESTCP by Dr. Andrea Leeson, followed by a list of upcoming webinars in the series. After Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's event features 2 award-winning presentations on environmental restoration projects. On today's call, Dr. Andy Martin from the U.S. Army Engineer Research and Development Center will present an overview of CERDP and ESTCP-funded research on applying hydrated lime to soils and surface water to immobilize metals and transform explosives. Dr. Martin's presentation will be followed by a brief question and answer session. Then Dr. Steve Larson, also from the U.S. Army Engineer Research and Development Center, will present research using a concentrated biopolymer to prevent soil erosion. We will conclude the webinar with an interactive Q&A session with both speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions in advance of that session. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line shown here. However, if you continue to have problems, please submit a comment using that chat box in the lower left-hand corner of your screen. And with that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of CERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Andrea has been with CERDP and ESTCP since 2001. Before that, Andrea was a research scientist at Battelle Memorial Institute, where she conducted research on in situ bioremediation. Andrea?
Thanks, Jennifer, and welcome everyone to today's CERDP and ESTCP webinar. First, let me just give you a little overview on both of the programs. CERDP is the Strategic Environmental Research and Development Program, and we were established in 1991 by Congress. And it's a partnership between the DoD, the Department of Energy, and the EPA. Our mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. And we fund both fundamental research as well as advanced technology development, the goal being to ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, and here we demonstrate innovative environmental and energy technologies. These investments typically capitalize on past investments under CERDP, or it can be from other research programs, and they're designed to transition technologies out of the lab and into the field. Especially important in all of our ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs, so much of the CERDP research occurs at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally we do support lab efforts under ESTCP. We have 4 program areas in CERDP and 5 in ESTCP. The Energy and Water program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapons System and Platforms, are CERDP and ESTCP programs that are managed jointly by a designated program manager. Our webinar today is focused on research and demonstrations that were conducted under the Environmental Restoration program area. Environmental restoration has essentially 5 main areas of research and demonstrations: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series will be highlighting research and demonstration efforts from each of the 5 program areas. And we've launched a new mini-series in 2017, which concludes with today's webinar, in which we were highlighting research findings from CERDIP and ESTCP award-winning projects. As you can see, upcoming webinars will cover a broad range of topics, including monitoring and risk assessment, environmental risk from munitions constituents in the underwater environment, 1,4-dioxane cleanup technologies at DoD contaminated sites, solutions for installations, participation in energy markets, and high-res site characterization of chlorinated solvent sites. You can find more information about our upcoming webinars at this link, and registration is now live for all of the webinars through the end of May. And finally, I am extremely pleased to announce that we are once again holding the CERDIP and ESTCP Symposium in November in Washington, D.C. Registration information will be available very soon on our CERDIP and ESTCP website. I hope you enjoy the webinar today, and Jennifer, I'll turn it back to you.
Thank you, Andrea. And now it is my pleasure to introduce Dr. Andy Martin. He is a supervisory environmental engineer and chief for the Environmental Engineering Branch at the United States Army Engineer Research and Development Center's Environmental Laboratory. His research focuses on range management, remediation, and sustainable operations. He received his Bachelor's of Science degree from Purdue University in Chemical Engineering, a Master of Science degree from the University of Illinois in Environmental Engineering, and a doctorate from Purdue's Department of Agronomy and the Ecological Sciences and Engineering Interdisciplinary Graduate Program. Andy?
Good morning. I'd like to thank Dr. Leeson and the CERDIP ESTCP program for giving me the opportunity to present on this project, Grenade Range Management using lime for the dual role of metals immobilization and explosives transformation. First, I have to recognize all of the colleagues, the group of researchers, students, and installation support staff that helped us make this project a huge success, and I would like to thank them for their assistance. This project is based on two main ideas: that increased alkalinity caused by lime addition to soil will, one, decrease heavy metal migration, and two, base catalyzed transformation of explosives, such as RDX and TNT, will eliminate or reduce their migration off the range areas. Slide 17, please. Here's the agenda. In general, I will go over the project goals, basic concepts behind the alkaline hydrolysis effort, our results, and the lessons we learned from the project, and conclude with the benefits to the Army and the DoD. Slide 18. On the right, you will see a picture of a hand grenade residue that was collected from a blast chamber study published by Larson et al. In 2009. Much of the material you see is a metal casing that surrounds the explosives material, in this case composition B. Fragmentation grenades typically contain composition B at about 60% RDX, 39% TNT, and about 1% wax binder within a steel shell casing. The majority of the hand grenades thrown on hand grenade ranges are used with this type of composition B. You will see clearly the spoon in the upper right corner, the safety clip and springs in the top center that are part of the hand grenade. What you do not see is much of the explosive residue, in essence RDX and TNT, that manages to get on the range from non-detect to an average of 0.37 milligrams. For instance, if you are throwing several thousands of grenades, the munitions constituents, or MC, can quickly add up. This project is based on the premise that increasing alkalinity caused by lime addition to soil, like I said before, will, one, decrease water solubility of heavy metals present in the soils, and two, the base catalyzed transformation of explosives, or RDX and TNT in this study, significantly reduced or eliminated the migration of RDX and TNT-based explosives. Slide 19. Next slide. There are many DoD training areas, impact sites, that are or could be affected by the migration of MC from an area. You'll see in this picture, or in this slide, there are 7 different pictures. These include former munitions manufacturing sites in the top center, training ranges such as hand grenade ranges and open burn detonation areas in the upper right corner and the lower left corner, blow-in-place or BIP facilities in the lower center, and formerly used defense sites, FUD sites, in the lower right corner that typically contain RDX and TNT or other munitions constituents residue on them. Slide 20. So what is alkaline hydrolysis? In the figure, you have a schematic of the process for alkaline hydrolysis. In general, it is the use of elevated pH to use additional hydroxide ions to interact with organics to break them down. In this study, the addition of lime, a lime source, or hydrated lime calcium hydroxide, was used to elevate the pH above 11 to induce the breakdown of explosives. In this case, RDX and TNT, and also stabilize the metals that came out of the munitions constituents in the soils. Hydrated lime was chosen as a soil amendment for its ability to increase soil pH into the range soil necessary to transform explosives to environmentally friendly end products and for its ability to stabilize the metals. A note of caution, the alkaline hydrolysis reaction does not occur in the absence of water. So you either need to apply water with the hydroseeder, hose, or wait for a rain event. And after that, a few things need to happen for this to occur. One, the lime has to become soluble in the pore water. The munitions constituents, RDX, TNT, metal, also need to become soluble in the pore water. And finally, the hydroxide ions and the MCs need to find each other in the pore water to react, for this reaction to really take place. This is not impossible, but when the conditions are set, they can facilitate this as a viable management approach for range managers. Next slide. Slide 21. Prior to the field implementation, we wanted to ensure that the degradation of RDX and TNT would occur under high pH. As mentioned, moisture content is a key component to ensure this occurs. With RDX on the left and TNT on your right in this figure, the plots show the degradation at elevated pHs above 11. For RDX, a pH of 12 and TNT, a pH of 11.5. In both laboratory studies, under ideal conditions and mixing scenarios, there was a rapid degradation of the parent compounds using alkaline hydrolysis. The transformation of TNT in basic solution was established in 1891 by Janowski. More recent studies have determined that a variety of explosives and energetic compounds, such as RDX, can be degraded by alkaline hydrolysis or alkaline destruction. Additional studies have shown that the application of calcium hydroxide to solution and soils containing TNT and RDX will result in breakdown products such as nitrate and nitrites. Slide 22. We looked at the mineralization potential of explosives post-liming event using carbon-14 labeled RDX and TNT. The results for RDX are shown here, with the control on the top, primarily the red, and the treated on the bottom, primarily the black shaded circle. Similar results were observed for TNT. In essence, we observed minimal mineralization of the control, but over 75% mineralization of the alkaline hydrolysis treated samples for RDX, resulting in non-toxic, low molecular weight compounds such as carbon dioxide and formate. Next slide, slide 23. Slide 23, please. For our studies at active hand grenade ranges, we needed to develop a rapid lime application method so that we did not affect the current training activities on the range. This was very important to the installation that we partnered with. It was determined during the treatability study that an application of 1% lime by weight was needed to elevate the range soil above the desired pH of 11.5. At the hand grenade range, this was roughly 1 ton of lime per acre mixed in at a depth of 6 inches. We applied enough lime to elevate the range impact soil to above a pH of 11.5 for an extended period of time. In this case, we were looking at a 3-month time interval. As seen in the picture, we used a drop spreader to evenly distribute the lime on the first application in the impact area, and then used a rake towed by an all-terrain vehicle, or ATV, to mix the lime into the soil at depth. We looked at other methods to apply and mix the lime, eventually relying on the grenade detonations to continue the mixing process. Slide 24. As mentioned, several techniques have been tested at the hand grenade range and at an open detonation range to apply the lime in the bays. These varied from simply opening bags on the range by hand and raking them in to a uniform color distribution using a drop seed spreader, such as the one seen in the upper right picture. In order to mix the lime into the soil to the required depth, several techniques were evaluated, including a garden rotor tiller, a disc, such as the lower left picture, towed by the tractor, a cultivator, and even hand rakes. A hydroseeder was also used during the final lime application at the hand grenade range in order to evaluate the effect of consecutive liming and watering on dust control. Slide 25. Slide 25. At the open detonation range, we used a drop spreader to initially lime the range, as seen in the previous picture, and the entire range to develop a baseline soil concentration. Basically, we treated the entire range before we did the follow-on demonstration there. We also looked at the ability for the lime to be dispersed with the blast at the open detonation range, where 500 to 1,000 pounds of explosives were filled into a hole and then piled on top with some additional soil, as seen in the top picture here. We placed about a ton of lime, 50-pound bags each, around the outside of the pile of soil, and then detonated it to disperse the lime with the blast. The bottom picture shows the range post-explosion. Slide 26. Here we'll go into some of the results, starting with slide 26. Next slide, please. For the hand grenade range, we selected 2 of 4 throwing bays, roughly 1 acre in size, that were separated by 2 earthen berms with another bay in between. We did this so there wouldn't be any cross-mixing of the lime with the control bay. RDX soil concentrations in parts per million, milligrams per kilogram, were determined through the EPA method 8330 by collecting and analyzing multiple 25 to 30 point composite grab samples from each bay. 2 RDX concentrations. The RDX concentrations of the control bay or unlimed bay are in red in this plot, and the lime bay in 2 shades of green are the pre and post liming. The lighter color is the pre-lime, and the darker color green is the post-lime. As seen in the plot, there is a downward trend toward the non-detect RDX concentration in the post-lime soil samples that were compared to the pre-lime soil samples. Slide 27. Surface soils were collected from an open detonation area in another alkaline hydrolysis study, as I discussed before, that was also supported by ESGCP. As seen in the plot, there were detectable levels of explosives in the soil prior to the pre-liming event. Then after the liming, there was only 2 hits of RDX in the range soil that we collected, similar to what we did on the hand grenade range. You also see that the concentration was going down with the RDX after every post-liming event. Slide 28. Not only was it important for us to look at the soil concentration, but we also wanted to look at the pore water concentration of RDX and TNT from the hand grenade range. So we installed suction lysimeters, roughly 5 5 to 7 feet below the surface of the grenade range impact areas. Pore water samples were collected on the range on a regular basis as long as the lysimeters were working and weren't impacted by the actual detonations of the grenades. As seen in the plot, the addition of lime significantly reduced the migration of RDX compared to the control down to the depth of the lysimeters. Slide 29. We also wanted to evaluate the pore water lysimeter metal concentrations. So we looked at the metal concentration of nickel, zinc, manganese, and molybdenum that are typically seen in the RDX or the grenade range shells. And we saw a reduced migration of metals in the limed versus control areas. Slide 30. Lessons learned. There are 3 key lessons learned that I want to focus on from this project. They include 1, lime is an effective management strategy. 2, low-cost treatment approach. It is a very low-cost treatment approach. And 3, there are some factors to consider with lime application. The use of lime transforms explosive compounds into benign products. We've seen that in the lab and also in the field. It stabilizes metals in the range soil. It reduces off-site migration of the munitions constituents, both as surface water, soil, and groundwater. It also reduces the potential of future liability associated with migrating MCs by providing a management approach for range managers to treat the source area. Slide 31. In the hand grenade range study and project, we were able to treat 1 acre for a little over $2,000 an acre for 3 months, depending on the range conditions and rain events that occurred. Lime is relatively inexpensive and readily available. The cost that we came up with also includes labor, materials, and other stuff such as equipment that you may need on the range. The liming did not require special training, but it is recommended that one use the proper personnel protective equipment, PPE, when handling the lime. I suggest reading the safety data sheet if you plan to use lime as a management approach for your ranges. On multiple occasions, we took several different crews on purpose to the hand grenade range to lime the impact area, and the time required to lime an acre was less than an hour. This also included sampling events at the same time, and this was with the novice crew on multiple occasions. Slide 32. There are several factors that affect lime application that include soil particle size, range use, and unexploded ordnance or UXO clearance procedures. This is a really important thing to remember when accessing any impact area, to be properly trained and understand the risks associated with the specific ranges you are dealing with. UXOs are not friendly, and they don't care. Munitions constituents present at the range to include explosives, RDX, and TNT concentration in the impact area soil, and most importantly, the annual and seasonal rainfall events and amount, as discussed earlier, is important to determine if there is enough moisture or pore water for this to be a viable management approach. Slide 33. The migration of metals and explosives in both soluble and particulate form from the impact areas of the ranges occur through a variety of mechanisms, including 1, transport in surface water following rain and storm events, 2, transport or soil particles following rain and storm events, and 3, leaching through the subsurface towards groundwater. Effective management of explosives and metals requires an understanding of the natural and engineered processes controlling their fate and transport at the sites. This project is based on the premise that increased alkalinity caused by lime addition to soil, 1, decreased water solubility of heavy metals present in the soil, and 2, base catalyzed transformation of explosives, in this case RDX and TNT, will be significantly reduced or eliminated from the range area. Slide 34. I would like to thank Dr. Leeson, CERDIP, and ESTCP for the funding that supported this project and for giving me the opportunity to present today. The interesting results were observed, and many interesting results were observed from this project. I would also like to thank all of the researchers, students, and installation support staff that helped to make this project a huge success. Without their countless hours of sample collection, sample prep, and data analysis, we would not be able to tell this story. If you have any other questions, I can be reached at andy.martin@usace.army.mil, and my contact information is on this slide. I'd be glad to take your questions.
Great. Thank you so much, Andy. We have received a number of questions from the audience, and I would just like to remind our audience one more time to submit questions by using the chat box on the left-hand portion of your screen. The first question is from the California Department of Toxic Substances Control, and the question is about reversibility of lime treatment. Is lime treatment reversible?
Yeah, over time, the soil will naturally go back to its the pH that it started at, or just a little bit above it, through regular interactions with the atmosphere. Carbon dioxide will infuse into the soil, and eventually the alkaline hydrolysis, or the elevated pH, will go back down. And we saw that at the limed ranges. Over time, we got up to a pH of 11 to 11.5, and when we went back after 3 months, the pH had already dropped back down to about 8 or 9. So over 3 months, we saw a huge decrease in the pH just from natural weathering effects.
Thank you. The next question is from US EPA. At what depth can pH 12 soil conditions be achieved to obtain significant explosive degradation?
In this scenario, we're looking at a topical application going down as deep as really a disc could plow into the soil and not disrupt too much of the range. So it was anywhere from 6 to 8 inches. You could probably get down to 12 inches depending on the soil conditions. If you really wanted to mix deeper, you probably could, but that would require a lot of earth moving. And in this case, we didn't want to disturb the impact area any more than was necessary. One, because we didn't want to impact the active training that was going on in this range. It was an active range. And we also didn't want to bring in a lot of heavy equipment to do that work. And we were trying to find a low-cost alternative to just treating the source zone.
Okay, thank you. The next question is about the slide that is being shown now, slide 26. And the question is, why is there so much variation in the RDX concentrations over time? And was the concentration of RDX decreasing over time in the post-liming bay?
So the first part, why is there variation? This is an active range. They're actively throwing grenades out on the range. It's disturbing the topsoil down to 3 to 4 feet. It makes craters, and then the range management approach was sometimes to come back and reapply soil or fill in the craters. So the pH change based on that towards the latter end of the study. Also, you have migration of the RDX off range, either through surface water or through the pore water migration. The other aspect, could you repeat the second part of the question?
Was the RDX concentration decreasing in the post-lime bay?
Yeah, the RDX primarily went into the water, so you could say that it was decreasing, but they are still adding more grenades, so they found a happy medium there. It does look like from the plot, and these again are soil concentrations, grab samples, so sometimes we got a hit of the RDX and sometimes we didn't, and that's where you get some of the variation. That's why you see the standard deviation is really extreme on some of these samples. But not the water. This is not the water.
Okay, thank you. Are there opportunities to use this approach on undisturbed ground where tilling is not an option, like tundra, to address metals from things like fugitive dust that have migrated into surface soil?
I don't know if that would. Yeah, you could apply lime, but I don't know if without mixing it in, if you're going to have a good interaction with the hydroxide and the fugitive metal dust. It may stabilize it for a while, but it's something we didn't really look at, just a topical application.
Okay, thank you. As the pH returns to its original value over time, can metals become remobilized from the soil?
Yeah, that's a tricky question because it really depends on the metal and where it falls in the stability range of the pH. Some metals are more stable near neutral, like lead, and some are more stable near a pH of 7 or 8, depending on what their interactions are. So that's a tough one to answer, and it really depends on the metal that you're talking about. But in this study, we saw a fairly good stability.
Okay. We've received a couple of questions about how this treatment approach would affect groundwater. So in general, how would amending surface soil affect groundwater? And then specifically, how does it affect the pH values in groundwater?
Yeah, so that's a great question. As you saw in the slide with the pore water concentrations, we saw a huge reduction in RDX going down just 5 feet into the suction lysimeters. And over time, I think you would see that same decrease of RDX going into groundwater sources. And that was the ultimate goal here, was to keep RDX from migrating down into the groundwater or to surface water. The other aspect is when we checked the pH of the pore water down the suction lysimeters, it was already down at near neutral, 7 or 8, the pH range. So even just going down 5 feet, the pore water pH concentration went down drastically. So once it gets to the groundwater, it should be stabilized or near what the groundwater pH would be.
As a follow-on question to that, Andy, how effective is the surface liming if the groundwater is already contaminated with explosives like RDX?
It probably will not affect what's already in the groundwater, but what it will do is keep additional RDX or explosives from migrating into that surface or groundwater plume from the surface. So this is more of a management approach to reducing the risk, but the groundwater issue is something that probably needs to be addressed differently with a different technology.
Okay, thank you. The next question is also from US EPA, and it's about slide 27. The question is, why were RDX concentrations higher after the initial lime application?
Yeah, remember when I talked about the reaction having to occur in pore water, the lime getting into the pore water and the metals getting into pore water, RDX getting into pore water. After this initial liming event, they had low rain events, so the RDX concentration built up over time because it is an active range to the 1.8 parts per million you see here. And then they were able to see rain events after that, and that's part of the reason why the concentrations went down. So it's kind of it all depends on when you sample and what's actually occurring out in nature and how the particulates are migrating to make the reaction happen with the lime.
Okay, thank you. Does alkaline hydrolysis work on other explosive compounds besides TNT and RDX?
Yeah, that's a great question, and it does work on RDX TNT and some other compounds. And some of the newer munitions are trying to see if it works with that. DNAN is definitely an issue, and we have active research to see what's going to happen there.
Okay, thank you. Since TNT is hydrolyzed more easily than RDX, did you see more complete TNT degradation in the field? And if so, could it be a surrogate for RDX or vice versa?
We actually saw more complete detonation of the TNT than the RDX in the hand grenade range or hand grenade residual study. There was very little TNT in the grenade residue. TNT also, even though it is more soluble, it tends to sorb more readily to the soil particulates, so it migrates less. So it's really not a very good surrogate for RDX contamination.
Okay, thank you. And we have just a couple more questions for this session. The next question is about sediment water partitioning coefficients. Have partitioning coefficients for RDX been established at the field sites for this study?
Not for this study. We have done other studies with looking at the partitioning coefficients, and if someone wants to send me an email, I could probably send them information on that.
Okay, thank you. The next question is about the granularity. Composition B is generally deposited as granules, and so does that mean that the degradation would be superficial to the granules?
Again, it requires the granule Comp B to dissolve into the pore water, and then for it to find the hydroxide and actually the reaction occur. So you'll still have the granules out there, but over time they will dissolve. And the smaller they get, the quicker they dissolve, so you'll see higher concentrations in the pore water. So yeah, it doesn't necessarily attack the granules.
Okay. And then the final question for this question and answer session, do you see an application for this technology outside of DoD?
Yes. Anywhere where they're using explosives like RDX TNT or comparable explosives that work with alkaline hydrolysis in construction, in mining, civilian ranges, other facilities that may manufacture RDX and TNT components, former facilities. There's definitely application outside of the DoD.
Okay, thank you very much, Andy, for the wonderful presentation and for answering all of these questions. To the audience, Andy will return at the end of the seminar to address more general questions or any additional questions from the audience. The next part of the webinar will be presented by Dr. Steve Larson, a senior research chemist with the United States Army Corps of Engineers. Dr. Larson serves as the Engineer Research and Development Center's Environmental Laboratory Engineering Branch in Vicksburg, Mississippi. His current research includes the study of biopolymers and the growth, extraction, and identification of potential uses for biopolymers in the environment. As principal investigator on several grants ranging from military munitions to modernization of the Army industrial base, Steve has studied heavy metals, metalloids such as lead, antimony, and tungsten, and insensitive munitions in soil and water. He has authored more than 50 peer-reviewed publications, numerous technical research reports, and patents. He earned a bachelor's degree in chemistry from Davidson College and a PhD in physical and inorganic chemistry from Colorado State University, Fort Collins, Colorado. Steve?
Well, thank you very much. Yeah, that was a long time ago when I earned that degree. So yeah, today we've got the pleasure of talking about a biopolymer that we use for erosion control of protective berms. So on the agenda for today, what is the challenge? And the challenge it's similar to the previous presentation, and that is geoengineering surface soils for a desired purpose. And in this case, the purpose was holding an artificial slope, and that wraps up a number of different soil properties. It deals with reduction of erosion, sediment transport, those types of issues. So the general idea of environmentally engineering a soil by using soil amendments in order to get desired soil properties is the challenge that we're talking about today. And of course, there's many solutions to this to these issues. Today, we want to talk about a specific biopolymer that we've been able to produce on an industrial scale for use as a soil amendment that we can then mix into the soil and change soil properties. So we'll discuss what a biopolymer is, how it's produced in nature, and also how it's produced on an industrial scale in order to geoengineer the surface soil. We've got a number of examples of where it's been used, both in the ESTCP demonstration program and in the past few years since that demonstration. And we'll talk a little bit more about additional biopolymers that are under development and potential uses for those compounds, and then wrap things up with the benefits to the Army and the DoD. So slide 38. As I mentioned, the challenge here is geoengineering of surface soils, or modifying surface soils as you find them in the environment in order to serve a specific purpose, and whether that be degrade RDX in those surface soils before it leaches down into groundwater, or reduce erosion from a steeply sloped berm area. So military facilities require a number of sustainable environmentally sound management techniques in this area. So, of course, we want to eliminate or reduce sediment transport off-site from these sites. We want to eliminate or reduce dust production. We want to maintain berms many times at artificially steep slopes, reduce wind and water erosion from roadbeds and training areas. This turns out to be a very expensive problem at many of our installations. And we want to do all this stuff, in many cases, in a compatible mode with vegetation. And that's going to be one of the keys to the discussion today, is how do we geoengineer surface soils in a way that they're still compatible with plant growth. So slide 39, please. So when we talk about modifying surface soils from a polymer addition standpoint, there's been a lot of work done and a lot of products out there that are petroleum-based polymers, and they're currently used as soil amendments for a number of engineering purposes. In some cases, the costs are high. In some cases, they biodegrade very slowly. It all depends on the specific polymer. There might be some toxicity associated with the unreacted monomers present in the polymers, and in general, they're based on non-renewable materials, the petrochemical industry, in order for their production. But the main issue in a number of the situations is this is the low compatibility with plant life. So you're stuck with an either-or type of a situation. we can lock the soil in place so it doesn't erode when water runs down the slope, but in doing so, we don't have any plant life on the slope because the polymer that's holding the soil together isn't compatible with the plant life. So slide 40, please. As far as a solution on that, is the use of biologically produced polymers. And the big benefit of these biologically produced polymers is that because the polymers are produced by soil bacteria that originally evolved to produce these materials in a symbiotic relationship with plants, they have high compatibility with plant life in the system. So we can get a mechanical stabilization by the application of large amounts of these polymers to soil and still have compatibility with plant life. In some cases, we can produce these and use them at lower costs relative to other soil additives. Their persistence in the environment may be lower than petrochemically based polymers. We see non-toxic end products of that biodegradation. And one of the really nice aspects of the biopolymers is a potential storage of what used to be atmospheric carbon in the soil. It's also referred to as soil carbon sequestration, which has the potential for reducing atmospheric or either reducing atmospheric carbon dioxide levels or reducing the increase. Slide 41, please. So the title of this slide, what is a biopolymer? Maybe a better question to ask is, how do plant systems engineer their soil environments? And one of the ways that plant systems do this is by working with a symbiotic soil microbe. So you've got a two-species system where the plant is feeding the microbe, and in return for that benefit, the microbe is producing an EPS, or an extracellular polymeric substance. So the microbe, in the case that we're talking about today, is a common microbe, Rhizobium tropici, that it infects the root area of the common bean or legume type plant systems. So these two living systems work together in order to engineer the soil system for the net benefit of both species. And this is the way that over the course of decades or even centuries, that soil changes from very low quality soil to higher quality soil. Is through year after year of these interactive systems, increasing the soil organic carbon content and providing beneficial soil behavior that benefits the two systems. So what we were able to figure out how to do is to take this out of the soil and produce the EPS on an industrial scale. So on slide 42, what we were able to do is to take a monoculture of the Rhizobium tropici and produce it in larger and larger bioreactors, and in that way essentially trick the microbes into hyperproducing the EPS. And this takes the process from a very slow process that happens seasonally just in the root zone of specific plants, and now we're able to generate a material in large volumes that we're able to apply to soil rapidly, so that essentially overnight we can impart the same type of change in soil properties that would happen over decades of leguminous plant growth. So we're very excited about this new industrial approach to changing soil properties. And on the next slide, slide 43, we see a couple of the soil properties that we were able to affect by the addition of biopolymer. So on the left, we set up a number of soil systems with steep slopes, and rained on these slopes once a week for 16 weeks. And over the process of the 16 weekly rain events, measure the amount of soil that was remaining in the steeply sloped portion of the cell. And what we found was that for the two highest dosings of the biopolymer, we retained all the soil on the steep slope, and for a lower dosing of biopolymer, we saw a significantly smaller loss of slope compared to the two control soils, where essentially the soil returned to its to the angle of repose that it would naturally want to have. And then we saw similar results when we evaluated wind erosion, as we see on the right. And what this is evidence of a similar type of mechanical soil stabilization that we get when we consider the use of the petrochemical soil polymers for surface soil amendment. But the exciting thing about the biopolymer is its compatibility with plant life. So on slide 44, we see some of the laboratory information that we got with regards to compatibility with the plant life. So on the left, we were able to look at the germination rates for specific seeds with and without biopolymer, and found that the biopolymer enhanced the rate of germination of seeds in soil. And we're also able to do simulated drought studies on plants grown in soil with and without the biopolymer, and saw that the presence of the biopolymer actually allowed the plants in the treated soils to withstand drought to a greater extent than untreated control soil. Slide 45, please. So one of the most interesting aspects of the way plants behave in biopolymer treated, the Rhizobium tropici biopolymer treated soil compared to control soils has to do with the root development and architecture. And the photos along the bottom are quite interesting, because the plants that grew in the biopolymer treated soils had a much greater amount of root tissue developing than what we saw in the control soils. And we see this over and over again. So when we start talking about producing or maintaining steep slopes on army installations, what we are noticing developing is essentially a self-renewing biogeotextile, or a root map along the surface of the soil that for individual plants helps hold the soil there in the root zone and acts as a stabilizing aspect for the soil. And then when adjacent plants' root structures start to intertwine we get a more homogeneous layer of protection that helps hold the material together. So this is where the compatibility between the mechanical stabilization that we note from the biopolymer being present in the soil, coupled with the plant-based stabilization or development of this self-renewing biogeotextile becomes very exciting as a tool for holding soil together, for reducing erosion, maintaining steeper slopes, eliminating fugitive dust, the types of issues that we want to address with these types of technologies. And before I leave this slide, the other very exciting thing about this is a very effective tool at pumping carbon dioxide from the atmosphere into the subsurface, because we're in biopolymer amended soils, we're able to generate very large concentrations of organic carbon within the subsoil, and of course all that carbon originated in the atmosphere, and we're very excited about this as a potential tool for soil carbon sequestration. So on slide 46, I want to get back to where this biopolymer has been used, and start with military field application. This was the subject of the ESTCP demonstration, and there was an explosion protection berm at Iowa Army Ammunition Plant that had undergone a number of years of soil slippages, and the height and shape of the berm had gotten so low that it no longer provided the explosion protection that was needed for the site. So we were able to go in and reform the berm into a height and shape that was adequate for its intended purpose, and also treat the berm with a number of different application approaches using the biopolymer. So there on the left you see the application of the biopolymer using the fire hose application technique, and below that the berm after it's been reshaped. On the right, we have a control section of the berm with no biopolymer added, and then we have two surface additions on that side, a single application with a low-level application of the biopolymer on the surface, and then another double application with twice as much, and then the entire right side of the berm, as you see it on the screen, was a high-dose application of biopolymer that was mixed into a depth of 6 inches. So we were able to form this berm in the spring of 2011, and got the initial visualization of the 3D shape of the berm, and that way we're able to measure the surface changes of this structure over time. So on slide 47, we see the surface changes over time. So A shows the changes in the first 6 months of the lifetime of the berm, where the blue ring around the toe of the berm is where soil is being added to the to the soil surface, and then the yellow and the red show the areas where the soil is being lost. And then in B, we were lucky to be able to come back again in August of 2014 and actually look at the changes over a period of 2.5 years, and we were able to note a significant soil disturbance there on the left side of the berm, that red and blue blotchy area that we see in B. So on slide 48, we'll get the calculations of the soil mass loss by treatment area. So just like we saw in the laboratory study, The unamended control lost the most soil mass area per area, and the single application on the surface, we saw significantly less soil mass loss, and then it stair-stepped down through the applications, with the double application mixed into a depth of 6 inches, providing the least soil mass loss per area. So this compares the soil loss after 6 months, and we used the LiDAR tool in order to develop the three-dimensional imaging in order to collect that data. On slide 49, we see another visualization tool based on the LiDAR data. And it's a very interesting way of evaluating such a large berm. But what I want to point out is that on the left side of the berm, in the pictures that you're seeing, we measure an extensive amount of leveling and smoothing of the berm surface over time. And this leveling and smoothing is very important from a runoff perspective, because what we don't want to get is ruts or channels where the water will preferentially run down the face of the berm. That's one of the big causes of the landslips, which was the failure mechanism of the original berm. We want the surface to remain smooth so that we get more of a sheet flow of water moving down the surface, and avoid this preferential water flow that essentially cuts out sections of the soil. On the right side, on the bottom, the 2014 image, you notice the large disturbance, and that occurred in the spring of 2014. On slide 50, we've got some actual photos of this landslip. So this is the type of landslip that made this berm need to be repaired in the first place. And these types of landslips were occurring all across the face of the berm, and had actually dropped the entire height of the berm down to the point where it was no longer useful for its intended purpose. And this landslip occurred right on the edge of the control area and the double surface application area. But you can see the actual pictures on the top. The volume of this landslip was about 275 cubic feet of soil, and then on the bottom you can see the comparative difference as measured using the LiDAR tool to evaluate this landslip. And it's important to note that it's not just the landslip itself where we're seeing significant losses here, but to the left of the landslip in the control area, we've got considerable soil loss there as well. And what we expect to happen is that this landslip will continue to move towards the left and eventually require O&M costs to go in and repair. So slide 51, please. So continuing on, this explosion protection berm at Iowa Army Ammunition Plant, the cost drivers that we've identified for this technology definitely deal with the quantity of biopolymer required. Of course, that's related to the size of the structure that's being constructed. Delivery is an issue. Even though this is a concentrated product, it's still an aqueous-based material, and fuel costs become an issue for transportation. At this specific site, we had an issue coming back in afterwards and getting the grass seed hydroseeder and operator on board. But once we did get the area seeded, we saw the same types of enhanced root structure development in the treated areas that we're very excited about. And one of the, I didn't quite mention this earlier, but one of the practical applications of this enhanced root structure is that even when the mechanical advantages of the polymer biodegrade away, you still have this self-renewing root-based structure that holds the soil together. So that leads into the increased effective lifetime for a given structure and reduced O&M costs over lifetime for that type of structure. So on slide 52, I want to point out another demonstration that we've done. This has to do with civil works work area that the Corps of Engineers is also responsible for. And this was a series of setback levees that were constructed on the Trinity River south of Dallas. It's referred to as the Kaufman Levee. The reason why I want to point this out is it goes into the ease of application of this technology. So the contractor who constructed the levee also was charged with revegetation of the levee post-construction, and they used a simple and very common hydro-seeding approach to hydro-mulch or seed the surface of the levee. And we were able to work with them on the demonstration, and all they had to do is add the biopolymer solution to the hydro-mulch mixture instead of the same volume of water. So it was essentially a simple tank mix within the hydro-seed tank, and there on the bottom we can see some of the comparative results. So in the untreated control, there's a fair amount of green in that image, and I know it's difficult to see, but very little of that green is actually the Bermuda grass vegetation that was hydroseeded onto the site. It's almost all unwanted, weedy vegetation material that we don't want on that levee. And then underneath, we see the biopolymer treated section, and about 80% of the green present within that image is actually the Bermuda grass species that we planted on the levee. And once again, we want to see extended lifetimes on these levees by the presence of interconnected root systems associated with the Bermuda grass on the surface of the levee, holding the slope together and providing a level of armoring to deal with potential flood events. Slide 53, please. So the Rhizobium tropici common bean system is an upland symbiotic system that produces these biopolymers or extracellular polymeric substances. What we're doing is we're looking at other types of plant microbe symbiotic systems where large amounts of EPSs are produced. And our hypothesis is that when those systems occur, that's a system where the plant, coupled with the microbe, is trying to once again engineer its soil environment in order to enhance the soil structure for its own purpose. And the hope is that as we identify these symbiotic systems, if we're able to take that EPS out of the soil system that it naturally occurs in and produce it on an industrial scale, that we can start coming up with soil amendments for other purposes, such as enhancing plant growth in highly saline soils, whether that be coastal restoration efforts or even revegetation of hydraulic of areas impacted by salty hydraulic fracking fluids in the petrochemical industry. We've got a number of research partners through cooperative research and development agreements who work with us on these types of technologies for things like improving hydroponic yield for vegetable growth. We've seen some very exciting results in the agricultural yield, especially from marginalized lands. And we're also interested in restoration of riparian zones using biopolymers. Slide 54, please. So as I mentioned, there's a number of different applications to this type of research and technology development. Today we spoke mostly about, on the military side, the erosion control and dust suppression aspects of it, but we've also got ongoing work in the agricultural fields and on the civil work area side of things, and then along with that, the entire area of soil carbon sequestration for shifting the soil into a much more aggressive sink for carbon in the whole carbon distribution system that's associated with the greenhouse effect associated with carbon dioxide in the atmosphere. Of course, plants take all of their carbon from the atmosphere, and we usually think about the above ground portion of a plant as holding large amounts of carbon, but the flux on that carbon is actually quite rapid. Once those plants senesce in either at the end of their their lifetime or at the end of a growing season, they release that carbon back into the atmosphere fairly rapidly. But a portion of the carbon that they place below the surface of the soil, that has a tendency to stay within the soil system for for much longer periods of time, and there's a potential that we might be able to access that phenomenon in order to reduce the amount of carbon present in the atmosphere. So on slide 55, back towards the DoD benefits, what we predict using these technologies is lower project construction and maintenance costs for facilities. This comes primarily through lower O&M costs for repair, as well as longer effective use cycles for these types of protective berms, levees, and other types of artificially steep slopes that we may need on DoD facilities. We also see, mainly because of this enhanced root geometry, limited incidence of invasive plant species or unwanted plant species, and this type of technology provides a positive focus on Army land stewardship. So on slide 56, there's information on that people can get on this specific ESTC project, ER 200920, and contact information for me. And like Andy, I need to thank ESTCP for the funding and and the belief in such a wacky demonstration project. I'm happy that we were able to come through for them with a satisfactory demonstration, and the many scientists, researchers, students, and support personnel that that made the demonstration possible. So with that, I'll take questions.
Okay, thank you very much, Stephen. We have received a number of questions. And if the audience has any additional questions, please do submit them in the chat box at this time. First, Steve, what is the key mechanism by which the biopolymer enhances plant root development?
Yeah, that's a great question, and it's one that we're still working on. The best clue that we have at this point is that when we compare plant tissue from control soil with plant tissue from treated, that grew in biopolymer treated soil, we see about 50% reduction in aluminum within both the roots and the above ground plant tissue. And for those people who aren't plant aficionados, aluminum is an extremely phytotoxic metal to plants. And it's strange because almost all soils have very high aluminum contents. The aluminum silicate makeup of almost all soils is, well into the percent range. But the action of aluminum on roots has to do with the displacement of calcium on what they refer to as root nodules, or the little buds on the roots that are the very first thing that happen before you get a root branch or a new root coming out. So what we're working on in the laboratory, as funding allows, is trying to understand this the mechanism by which the biopolymer blocks this phytotoxic aluminum process. Somehow the biopolymer is either sequestering the aluminum in the pore water and keeping it from getting into the roots or into the plant tissues, as evidenced by the lower aluminum concentrations. And that's what we believe to be the mechanism by which you get these large root structures. I'm sorry for the long explanation, but it was a very good question.
Yes, thank you. The next set of questions is about other uses for biopolymers. First, a participant from the California Department of Toxic Substances Control is asking if they've been used for soil caps on landfills or contaminated soil containment areas.
Not to my knowledge. It has been used for revegetation of mine material, particularly in West Virginia area for coal mines. In that situation, they end up with soil that doesn't do very well at supporting plant growth, and they found that amending the soil with the biopolymer gets them revegetated, that disturbed soil revegetated quite quickly. There's been some work in Texas with the Denton landfill on the use of the biopolymer, but not as a capping type material. But certainly, when you think about capping of a landfill type area, the type of enhanced root mass structure that we're able to achieve would be beneficial to keeping the gases that might be escaping from those areas to a minimum.
What about, Steve, for agricultural purposes or things like prairie restoration? Have the biopolymers been used in those cases, to your knowledge?
Yeah, there's been a number of field studies on the agricultural side. So the Corps of Engineers was able to get a patent on the industrialization for production of this material, and there have been a couple of companies that have licensed that patent and used this material either as a soil amendment or as a seed coating, and taken that through independent agricultural field trials, and those companies are still moving forward and trying to develop this as an agricultural product. We've also worked with prairie restoration groups through cooperative research and development agreements, where they've seen benefits in taking native vegetation seeds and coating it with biopolymer prior to spreading it following negative events like forest fires, and they've had positive results with regards to getting native vegetation to revegetate areas.
Thank you, Steve. The next set of questions is about impacts to the surrounding environment and receptors as a result of the application of biopolymers. Have you seen, first of all, impacts to the groundwater as a result of its use, and are there toxicological concerns or ecological concerns related to the biopolymers?
At this point, we haven't seen any toxicological impacts. The closest thing that comes to from a toxicity standpoint relates to the pH of the material as it's applied, and that goes back to the production process. One of the tools that we use to kill off the Rhizobium tropicea in some production techniques is to elevate the pH, and that also gives us a way to concentrate the biopolymer, because it has it's less soluble in water at a higher pH. So that allows us to make a soluble salt of the biopolymer and eliminate some of the transportation aspects. But beyond just the regular toxic effects of elevating the pH, we don't see toxic effects from the biopolymer itself. It's a naturally occurring polysaccharide material, and it certainly has potential for increasing the amounts of suspended solids in surface water runoff post-application. With regards to groundwater, we might see increased soluble organic matter as the low molecular weight compounds leach towards the groundwater. So it's been applied at a number of sites across the country without any negative effects.
Okay, thank you. And at this time, we'd like to bring back our first presenter, Andy, for one or two broader questions. Both of these presentations dealt with engineering surface soils for specific DoD needs. Where do each of you see these technologies moving in the future? And we'll start with Andy.
Yeah, so this is Andy. The technology and the application that we did in the demonstration, we tried to make it as simple as we could for the range managers in terms of going out and applying it at the range, not interfering with the training on site. And I think because of that, it's a fairly simple approach. Agriculture has been using lime to elevate soil pH for a long time. So it's a common method out there. It's just getting it to the right pH to treat the contaminants that are in the soil. Where do I see this going? I think in terms of the DoD installations, and the DoD really need to get on board on how they want to manage their ranges, and whether they want to put the costs up front to fund low-cost ideas like this, or put the cost up front later down the years to actually treat the water in the groundwater that the plumes generate from some of the installations. I don't know, Steve?
Yeah, I agree with regards to alkaline hydrolysis, but on a larger level, I see a trend towards using soil as a more as a tool for engineering. Of course, you know, it's one of the oldest engineering approaches that humanity has. You know, agriculture is the use of soil on a large scale for producing food. But in my mind, there are many other functions that we can use soil for. So Andy started with the use of soil as a way of a bulk soil, as a way of cleaning contaminants out of water and keeping them from getting to the groundwater. And then we moved on to the second briefing that talked about amending soil in order to get plants to build larger root systems. I think that this whole idea of geoengineering and using soil as a unit op from an engineering standpoint is something that's going to go further. I'm a big fan of a number of the researchers who are looking at the use of soil for adjusting the carbon dioxide level in the atmosphere. I mentioned that a number of times, but when you're dealing with a mass as large as the atmosphere and wanting to reduce by percentage levels, say the carbon dioxide content of the atmosphere, you've got to use a tool that has, you know, a comparable mass. And in that game, it's either the oceans or the soil. And I think that this whole idea of geoengineering and using soil in order to make large-scale changes is going to continue into the next 20, 30 years of environmental engineering research.
Thank you, Steve. And on that note, I would like to thank both of our presenters today, Andy and Steve. Thank you for the informative presentations and for addressing the questions from the audience. And our next webinar is on March 23rd on Thursday, and that will present monitoring and risk assessment of environmental risks posed by munitions constituents in aquatic systems. This webinar will feature 3 speakers, 2 from the U.S. Army Engineer Research and Development Center, and one from SPAWAR Systems Center. Registration is already open for this webinar, so please visit the CERDIP and ESPCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.